Imagine you have a truck with a limited capacity and a variety of box types, each with a different number of units. Your goal is to load the truck to maximize the total units carried. How do you decide which boxes to prioritize? You're given an array of box types, where each box type is represented by a pair, the number of boxes available and the number of units per box. You also have a truck size, which is the maximum number of boxes the truck can carry. The challenge is to calculate the maximum total units that can be loaded onto the truck, respecting its capacity. A naive approach might iterate through each box type and then individually load each available box until the truck is full. This would involve nested loops, one for box types and another for the quantity of each box. For every box loaded, we'd add its units and decrement truck capacity. This is inefficient because it doesn't make smart choices about which boxes to load first, potentially filling the truck with low unit boxes. The time complexity would be roughly n*m, where n is the number of box types and m is the maximum number of boxes of any type, which is too slow. Space complexity would be big O of 1, constant time. The key insight here is a greedy one: to maximize total units, we should always prioritize loading the boxes that offer the most units per box. If we have a choice between a box with 10 units and a box with 5 units, and both take up one slot, we should always pick the 10-unit box. This suggests sorting. We'll sort the array of box types in descending order based on their units per box. Once sorted, we iterate through the box types. For each type, we calculate how many of these boxes we can actually load. This is the minimum of either the remaining truck capacity or the number of boxes of that type currently available. We add the units from these loaded boxes to our total and then decrement the truck's remaining capacity. We continue this process until the truck capacity reaches 0. Let's trace this with an example. Suppose we have box types: 1 box with 3 units, 2 boxes with 2 units, and 3 boxes with 1 unit. Truck size is 4. First, we sort by units per box in descending order. So we have 1 box with 3 units, then 2 boxes with 2 units, then 3 boxes with 1 unit. Our total units start at 0, truck size is 4. We look at the first box type: 1 box, 3 units. We can load 1 box, as our truck size is 4. Total units become 3. Truck size becomes 3. Next, 2 boxes, 2 units each. We have capacity for 3. We load both available boxes. Total units become 3 plus 2 times 2, which is 7. Truck size becomes 1. Finally, 3 boxes, 1 unit each. We only have capacity for 1 box. So we load one of these. Total units become 7 plus 1, which is 8. Truck size becomes 0. We stop. The final total units loaded is 8. This is the maximum possible because we consistently pick the boxes offering the highest unit density first, ensuring optimal utilization of truck space. You'll spot this greedy pattern whenever a problem asks you to maximize or minimize a value by making sequential choices, and each choice has an immediate, clear best option. Specifically, look for problems involving limited resources, like truck capacity, where sorting by a key metric, like units per box, guides the optimal decision at each step. The time complexity of this optimized approach is dominated by the sorting step, making it big O of n log n, linearithmic time. The space complexity is big O of 1, constant time if the sorting is done in place, or big O of n if an auxiliary array is used for sorting. This greedy approach is powerful for similar optimization problems. Try the next problem using this same pattern. Don't forget to like and subscribe for more DSA insights.